All right, a question that comes up a lot in chapter 11 is, well, we have all these tests to tell whether a series converges or diverges. How do we know what test to use? Sometimes it's a little bit of trial and error, so you need to know when to bail on a test and move on to something else. But a good exercise is to try to generate examples of tests of series where each specific test will work. Then you can sort of get a better grip on the inner workings of the series. I'll let you know sort of what's going on through my mind when I'm choosing to use a particular test, and give some examples of series where particular tests might be appropriate. So let's start with our divergence test. Divergence test is pretty quick, so it's worth applying to any series, but really any time if you think the terms are not going to zero. Remember, it's only a test for divergence. It never shows you that a series converges, but here's an example where it would work. Sum from n equals 1 to infinity of, say, n squared plus 2n plus 3 over 10n squared minus 6. This test would show that this series diverges because the limit is a tenth. All right, so anytime you think the terms are not going to zero, but it's really short, so if you apply it and you get a zero, that's okay, you can just move on to a different test. All right, what do we have next? Integral test. We really wanted it for the p-series, right? Now that we have our p-series test, we don't need it for that anymore, so integral test only comes up in specific instances. So they're pretty rare. I immediately go to times when you might be able to make a substitution. So for instance, this series, sum from n equals 1 to infinity, natural log n squared over n, right, where I could, for the corresponding function, make the substitution where u would be natural log, and then integrate from there. Integral test I don't think is going to come up very often. Again, my mind goes to these types of examples where there's some kind of substitution we could make. Now, comparison test can come up a lot. I'm talking about the basic comparison here. This is really if the series looks like geometric or p-series. So, for example, I have a series like this, sum from n equals 1 to infinity, infinity, 5 to the n plus n squared over 3 to the n minus 1. Okay, I can use the comparison, right? I can use the direct comparison here. 5 to the n plus n squared over 3 to the n minus 1 is greater than or equal to 5 to the n over 3 to the n, and compare to that geometric series to get divergence. Of course, we need to have the comparison going the right way, or we should use a different comparison test. So let me switch to another sheet here to talk about the limit comparison test. So, limit comparison test. So same as the comparison test. Okay, same as the basic comparison test, but use it if the comparison's tricky. Or non-obvious. Okay, so for example here, I might have something along these lines. Sum for n equals 1 to infinity, say 10n squared plus 2n plus 5 over, what can we do? 3n to the 4th minus 2n squared. Okay, something along these lines. If you try to do a regular comparison, I don't think we're going to get it pointing in the right direction, but we can do a limit comparison instead. So limit comparison should work almost virtually every time the comparison test will work. Okay, so that's something to keep in mind as well. Okay, so here we'd compare to, say, 1 over n squared, right, using the limit comparison test, and then we should be able to get convergence of this series. Okay, and compare to the previous example I gave for the comparison test, right? And think about why the comparison might not be why the regular comparison test, the basic comparison test, might not work out the way we want it to. Okay, with the comparison test in general, again, I need to be seeing things like exponential functions and polynomial functions in the definition of the series because I want something to look like a geometric or p-series, which I already know about and can compare to. Okay, alternating series test. Fairly straightforward. So alternating series test, this is nice because it applies in very specific instances. Consider it any time a series is alternating. So for instance, sum from n equals 1 to infinity, minus 1 to the n, say, I don't know, n cubed, plus 1 over n to the 4th plus 5n, right? Something like this. But anytime you see that power of -1, it tells you the series is alternating. At least try the alternating series test. All right, and finally, the newest test we have is the ratio test. What are some clues here? Anytime there's a factorial, I would certainly think about the ratio test first. And then anytime I'm dealing with different types of functions. So multiple different types of functions. I might consider using the ratio test. So when I say different types of functions, polynomial, exponential, factorial. Okay, and so here's an example: sum from n equals 1 to infinity, say 3n factorial plus n squared over 7 to the n plus 1. Right, something like this. This is where I might want to use the ratio test. Okay, so there's sort of a quick rundown of some ideas related to how we might know when to apply a certain test. Like I said, it's not an exact science, so you really do just have to try some things out sometimes. Know when you're using a particular test, when you should move on and try something else because it's not working out. That's perfectly fine, okay? Needing to apply 2 or 3 different tests before you find the right one is okay, and the more you do it, the better you get at identifying the correct test sooner. Also think about times when you can use different tests to achieve the same thing. Which test would you prefer? Is there one that's quicker or a little easier for you? And try generating your own examples like these ones, again, to give yourself a better idea of how to make this decision of which test. Keep working at it as we keep going through Chapter 11.